Hello, this is Sabbir Malli. The topic of our discussion in this video tutorial is modeling with the first order differential equation. In this particular video, we will discuss the problem of mixing solution. So usually this problem has this setup. This is a very general setup of this problem where we have a tub, and in that tub there is some solution, and that solution is contains some amount of substance, you know and then there is a some solution is entering into the tub, and there is a outlet in the tub, and there is some solution is getting out or exiting the tub. And usually problem asks what amount of substance is present in the tub. So if we denote, let's suppose we denote the Q2 is the amount of salt, amount of substance. Substance can be a salt or it could be any other chemical. Amount of substance at any time t. This is usually we would like to calculate that as this process is happening, as the liquid is entering and also the liquid is exiting at some rate, what amount of substance will be present at any time t. Or for example, if after 10 second or after 20 second, what amount of substance which will be present in the solution. So as you can see, some solution is entering, some solution is exiting. It means the rate of change, there is a rate of change, there is a rate of change of Q of t. This Q of t is going to change with respect to time as the solution is entering and the solution is getting out. And the rate of change we can calculate is basically by the rate at which the solution or the substance enter, and we're going to subtract it from the rate at which the same substance, which I can basically Q of t, exit. So now further, the rate of enter, the rate of entering the solution or the rate of enter, that can be basically calculated by flow rate, how much solution is entering, at what rate the solution is entering, times what is the concentration of the substance in the solution. I'm going to just say concentration, but that means the concentration of entering solution, entering liquid or solution. The same thing is the rate of exit, at what rate the solution is exiting, rate of basically Q of t, the exit, is same as basically the flow rate at which basically rate the solution is exiting, and it's time the concentration, but this time this is the concentration of exiting solution, concentration of exiting solution. So these are some basic of mixing problem. So this is very generic setting of any mixing problem. That mixing problem could be anything, but this is sort of a generic setting of this mixing problem. Now we're gonna take one really particular example and try to understand this generic setting, how we can take this generic setting and solve one particular real world problem. So here is the problem. The first I would do is I would read this problem and will try to draw a picture. Once I will have the picture, then I can set up these problems mathematically. So as you can see in these pictures, we have in this problems, we have a tub. You can read this problem, but I have already read, so I will just gonna write the things which I find on this problem. There is a solution which is a 100 gallon. Initially, there is 100 gallon of solution, and in this 100 gallon, there is a Q of 0. This is the amount of salt initially, and then there is a solution entering into the tub which is entering at a r gallon. So we put r gallon per minute. In 1 minute, we put r gallon of solution into this. And the concentration of the solution is 1/4, means 1 pound of salt per 4 gallon. So in 4 gallon, there is a one, if you collect the 4 gallon and you extract the salt, there is a 1 pound of salt in it. And now the solution is exiting, and the solution is exiting at a same rate r. So since the rate of enter and the rate of exit is same, it means in all time there will be a 100 gallon of solutions in the tub. So this is sort of the diagram of the problem. Now we will set up the problem. So we know the rate of change d over dt. Dt over dt is called a rate of change. And here q of t, qt is the amount of salt at any time. So let's me, what is the q of t? Qt is amount of substance. In this case, it is the amount of salt at any time t. So this is basically the amount of salt. And d over dt is the rate of change at which this salt is changing in the tub, and this is equal to the rate at which the salt enter and minus rate at which salt exit. And we are already know in the previous slide, the rate at which the salt enter is the flow rate times the concentration of the solution which is entering. So we know the concentration of the solution which is entering is 1/4. And then there is a negative sign. The rate at which the salt is exiting is also R. In this case, the concentration. So concentration is the amount of solution and then the amount of the salt. So we know that at any time the amount of salt is Q of t. And what will be the amount of the solution? It will be 100 plus we put r gallon, and we also take r gallon out. So it will be just a 100 gallon, because r gallon enter into the tub and r gallon get out of the tub. So if I just write this differential equation, d over dt, this is a q now, and then this is r divided by 4 minus r divided by 100 time q. As you can see, this is a first order linear differential equation. So I'm going to write in that form now. As you can see, this is a d over dt and q plus r divided by 100 time q is equal to r divided by 4. So this is a differential equation which is in the form dy over dt time pt y is equal to q of t. So this is a first order linear differential equation. This is also an initial value problem, because we also know that q of 0, the initial amount of salt in the tub was q of 0. So this is also an initial value problem. So we can basically when we find the solution, we can also find the particular solution of this problem. So next I'm going to use these linear theory to solve this differential equation. So for that, I'm gonna first erase this. So now we have this differential equation. So we know that in this differential equation, the value of P of t is equal to R divided by 100, and the value of Q of t is equal to R divided by 4. To find the integrating factor, we need to calculate e to the power, the integration of R divided by 100 time dt, which is equal to e to the power R divided by 100 time t. Now we need to write down the solution. Solution is going to be a q of t time the integrating factor, which is a R divided by 100 time t, is equal to integration q, which is R divided by 4 time the integrating factor R divided by 100t dt plus c. If I calculate the integration of e to the power 100 divided R divided by 100t, I'm gonna R divided by 4 time 100 divided by R e to the power R divided by 100t plus constant c. So I'm gonna move the exponential on one side. So this is gonna be a q of t, which is going to be is equal to 25 plus c time e to the power minus R divided by 100t, because e to the power R divided by 100t, it cancel out. Now we have an initial value problem because q of 0 is equal to q0, that is the initial condition. So this will be a q0. If I substitute t is equal to 0, then will be 25 plus c. So that means c is equal to 25 q of 0 minus 25. Q of 0 minus 25. So now I will write down the particular solution. So the particular solution is now q of t, which is equal to 25, and then plus the value of c is q of 0 minus 25 and e to the power minus R divided by 100 times t. Now as we can see, we can calculate the limiting value of the solution. Limiting values means when times goes on to infinity, what amount of substance will be present in the solution. So we can use the limit. We can say limit what if time is goes to infinity of q of t, or in other word, what is the limit as time goes to infinity of 25 plus q of 0 minus 25 times e to the power R divided by 100 times t. As you can see, this limit is 25 plus q of 0 minus 25 times 0, because as time goes to 0, exponential goes to, as time goes to infinity, exponential goes to 0. So this means the solution in that problem is 25. So what this mean is, if we keep entering the water with the concentration 1/4, and the solution is keep exiting with the rate R, with the same rate the solution is entering, with the same rate the solution is exiting, for a very long time, the amount of salt will be 25 pound in the tub. So that will be the amount of salt present in the solution. Let me also draw the plot of some solutions to analyze. what type of solution these are. So let's, for examples, we have the flexibility of the initial amount of salt Q of 0. So we know there is a 25 basically amount of salt. If I putting the amount of salt on the y-axis, it means I'm putting what is q is the amount of the salt on the y-axis, and then here is the time, the x-axis is the time. So I know that if I have initially, let's for example, if I have initially 50 gram pound of any salt, so in that case it means q of t is going to be 25 plus 50 minus 25 time e to the power r divided by 100 time t. So as time is going to increase, e is going to decrease, and then this e is going to decrease and this is going to decrease to 0. So it means the solution will be, as time is increasing and the solution is decreasing, and but it cannot decrease more than this number, which is a 25. That is the limiting value of the salt substance in the tub, and that justifies basically. And so really doesn't matter if I start from 50 or I start from 45, the solution will decrease and decrease to 25. And same thing, any amount, if I start with any amount which is more than 25, the solution, the substance in the solution will decrease and it decrease to 25. Similarly, if I start from 0, if I don't have any amount of substance in my solution first or in the water, then it will be 25. And since q of 0 is 0, so it's going to be a minus 25 e to the power minus r divided by 100t. But in this case, as this is going to 0, this number is going to go to 0. So it means the amount of the salt is going to increase, but it cannot increase more than 25. So because this number is 0, so there is a 25 here. Similarly, if I start from 10 pound, it will increase, but it cannot increase there. So similarly. So here, this number is very important for us. It's sort of like a stationary solution for our problem, that no matter how much salt initially is present in the tub, if we enter the solution with the concentration 1 over r, and the solution will exit and enter in a same rate, ultimately there is going to be 25 pound of salt in the tub, because there was initially 100, because there is initially 100 gallon of 100 gallon of water, and one fourth is the concentration. So one fourth time 100 is a 25. So that's why the 25 is a very important number which we get in this problem. Okay, this is the end of this problem. Next, I will give you the few quiz problem for you to practice uh, in this section. So here I have one first quiz problem. So in this case, I have given you R, and I have given you the initial amount of salt, which is a 50, because Q of L was 25. In this case, you have to calculate the final time T at which you are within the range of 2% of Q of L, which is at 25. Please pause the video for a few minutes and work on this problem. Here is quiz problem number 2. In this case, basically, you have to find at what rate is required if the final time do not exceed 45 minutes. Please also use the previous problem which I solved to solve this problem, and pause the video for 1 and 2 minutes and work on this problem. This is also the end of this video. Thank you very much for watching. I will come with few more videos on the modeling with the differential equations. So please stay tuned. Bye for now.